So you probably know this Oscar Wilde quote that there's two fools, those that give advice and those that listen to it. So now I am a fool in two ways. I will give advice to myself. So this is the softest talk that I've ever given. It's just some discussion around what to expect from math and ML collaborations. And, you know, I've been involved in 3 or 4 of these now. So, you know, been doing this for about 4 or 5 years. So I feel like I have some, like, you know, some track record. So some capacity to generate advice for myself. So I think most mathematicians, like many mathematicians that I talk to, just feel that like ML people will not be interested in collaborating, and this has just not been my experience at all. Like through interdisciplinary work, like in our university, there's all these people telling us, you've got to be interdisciplinary. Go and talk to the people in economics. But I think that it's very important to kind of push back on this a little bit and say that if you actually want a genuine interaction, this is really going to take years. And so, sure, I'm happy to do it, but it's going to take years. Yeah. Yeah. So when I began work with DeepMind at the beginning of COVID, we had 9 months of just kind of talking at each other and trying to find some common ground. Also, I think that it's easy to get into situations in which you're like, we want the following, and then, you know, it's someone else's job, and then nothing happens for a month, and then they do their job, and you've forgotten about the project, and then it's the ball's back in your court. And so the tighter the feedback loop, the better. So I remember there's one kind of golden time in the work with DeepMind where, like, I was working in the day, I was mainly Alex was doing experiments in the night, I was waking up. And even then I felt like the feedback loop was not ideal because of this kind of shifting of time zones thing. But I felt like we made like a lot of progress in that period compared to these kind of deserts of no progress when this feedback loop was not happening. And also, I think that it's important to be aware that in a lot of these projects, the actual ML, so the actual training of neural networks, takes some very small chunk of the time. So there's an enormous amount of time spent writing code to generate training data, typically, and also analyzing experiments. So, you know, another way of phrasing this is that if you would like to do something in this world, I feel like it's very good to either have a complicated maths problem and a very simple ML setup, or a complicated ML system and a very easy maths setup. You know, François' work on GCD or something, like the maths, we really understand how to do GCD. We're experts on GCD and number theory. But François' like really understanding transformers on this simple problem. And in the work with DeepMind on the combinatorial invariants, the architectures that we were using were very simple. Yeah. But the mathematics is very difficult. Okay. So don't push both at the same time. I mean, it's very typical, like it's kind of a running joke with Adam, I think, that like people just always want to apply alpha 0 on a maths problem. And, you know, and no one's managed to make this work yet. So this is just a kind of philosophical point, which is that, and this is something that surprised me, is that you're working with someone in machine learning and they don't deeply care about the problems that you care about. And, you know, it's like ridiculous when I say it like that, but it's kind of surprising to me. I'm like, oh my God, like we could, you know, if we just understand what's going on here, we could prove conjecture blah. And they're like, I don't care. Yeah. Like, but the conjecture blah is really important. I'm like, I don't care. At some point we had this like really amazing little formula, and I was like, oh, and then just no one worked on it. I was kind of like, what? I'm gonna work on it.
The other way around as well.
Yeah. No, absolutely. Like Petar at some point was like amazed at some possibility for graph neural nets, and I just couldn't appreciate what he was talking about.
Yeah. Okay.
It was truly the math, physics interface, and I think all of you was familiar with it like that.
So yeah, so there's no comment, there's not necessarily a shared currency of worth. And also, I think this is really important, is that if the work is genuinely interdisciplinary, then what you find important has to change. You know, if you want someone else to find what you think is interesting, you also have to find what they think is interesting. Yeah. And I think that's one of the beautiful aspects of the genuine interdisciplinary work, is that you also move a little bit, grow a little bit. Engineering. So engineering, one shouldn't underestimate. So, you know, it's a really obvious thing, but like, if you're not actually writing the code, you shouldn't tell someone that like something's really easy and they should have just, you know, done it the way that you want to do it. You know, there's almost certainly something that you haven't thought about unless you're actually writing it. Yeah, basic, like the more basic software engineering stuff that you know, the better. You know how to use GitHub, etc. This is really important. So particularly for larger teams, it's extremely, you know, I've seen this happen several times now. You have a team of like 7 people, and they're all like having weekly meetings and all coming with these brilliant genius ideas. And then like 2 people are doing absolutely everything. And that's a real problem because, you know, if the 5 other people think they're these great, you know, wonderful, fantastic contributing to this project, and the 2 people are just slowly getting more and more resentful. And it's, you know, I think it can like long term, it can lead to really major problems. So avoid this, try to avoid this. Also, just, you know, it's tempting to be like, oh, we don't really care how fast it runs, we're mathematicians, we just care about the end result. But this is really not the case because of that kind of feedback loop. Like, you need to see results of experiments. If experiments are taking 10 days or something, the progress is just going to be too slow for you to be able to see anything. Yeah, that's similar to above. Yeah, so like some attention to engineering is very important, but also one shouldn't be over optimizing. You know, like often, I mean, you know, there's that famous statement of Knut that premature optimization is the root of all evil. And I feel like I think it's very important when you're writing code to be like, how critical is this? Like I probably just write it as is, and then I'll profile it and I'll see if it's actually an issue, and then I'll spend 3 hours optimizing it or something. But it's very important to be able to profile, and it's also very important to spend that 3 hours, but it's also important that you don't spend the 3 hours optimizing something that contributes 0.01% to your runtime. Yeah, this is kind of unsolved problem, is that typically AI papers have lots of authors, and I'm not sure whether we're going to be able to do kind of stay in the realm of small science as mathematicians.
I'm going to talk a bit about that.
Yeah, and I think this is really, like, I want to stay in my lovely, you know, 2 to 4 person collaborations. Like, I love that. I love working in these small teams. I'm not sure how realistic it is, and I'd love it if people have suggestions about this.
But Jordy, when you say often there's 6 to 10 authors, are 2 of them doing all the work as in your previous slide, or is it because there's really 10 different parts of it that need to be done?
Yeah, I mean, I definitely feel like there's very clear power structures in AI work where the lead, like the kind of theoretical bosses do very little. But I also feel that like maybe there'll be 2 bosses, but then, you know, in theory, a lot of the rest of the authors are doing something, right? Or
Yeah, the main difference between AI and math, from my anticipating what I'm going to say, is that if you look at the list of the author, the youngest author in AI usually does all the work, and the senior author does very, very, very little. It's an exception when the senior author works. So it's slightly different. Then what's a bit complicated is that usually, yes, you have 6 people, but only 2 working. But the 4 others will want to compensate, and they can create an inordinate amount of work for the others by having new ideas, by asking for new, you know, by stating, oh, but this is not science, you should run your experiment this way, that way, that way. So,
Oh, by rewriting everything you do. Or by rewriting everything you
Or by writing, or by fighting about, correct English speaking, which is always a fun when it's a table of French guys. The winner is not always the one who speaks English. But you can get into, so not everyone works in the 6 to 10 teams. But when you get into paper writing or finalizing experiments, the larger the team, the more complicated it gets still.
There is also a question of funding, because at least in the engineering department, right, like students are very expensive. And so if you are writing a lot of grants to fund them, you want your name on the paper.
So another thing that's like, I think hard, like certainly hard for me to accept is that ML is very much an experimental science. And, people always ask me like, how wide should I make my neural net? I'm like, I've got no idea. You just have to experiment. Still don't have any idea. You just have to set up a system, sweep various hyperparameters, see what works best. There's no better answer than that. And that's somehow disconcerting if you have a mathematical soul, but you've got to get used to it. Hyperparameter sweeps are expensive, so it's great to have someone that can do it on a cluster. And yeah, being disciplined about experiments is like extremely important. And I don't know, like I feel like I still haven't gotten to the bottom of like the right setup, and probably Francois has the right setup. But one thing that my rule is that I just like one thing that's just crazy, and I'm sure half of you are aware of this, but if you're doing experiments, like everything is so clear the afternoon that you're doing it, and you're like, how can I possibly forget like, what hyperparameters I was doing then, and then 2 days later, you've just got absolutely no idea, and you've just torched an afternoon. And so like my current method, which is not great, but it works better than nothing, is just to like repeatedly screenshot loss curves and things like that and save them and explain to myself, like, this is what I was doing. These are the parameters that were used in this experiment, etc. Just have some record.
Taking notes.
Yeah, taking notes. Yeah, taking some form of notes and like being disciplined about taking notes is just absolutely critical. Yeah, some people use weights and biases and say it's very, very good. I've never used that. Oh, this is one just a basic point for mathematicians, which I kind of want to yell out on like from the rooftop if all the mathematicians were in Boston. It's just that GPUs are really amazing. So this is just like a silly thing I did this morning, which is like, so take the time, generate 1,000,000 20 by 20 matrices on the GPU, take the determinant and measure the time. So this means synchronize activity on the GPU and then take the time. So in 0.04 of a second, one can compute 1,000,000 determinants of 20 by 20 matrices. Absolutely amazing. And this would be very similar if I put here like determine all the eigenvalues or something like that. And I feel like pure mathematicians are not yet aware that for certain like tasks that you can batch in this way in linear algebra, GPUs are just unbelievably strong. And this is some stuff that I was mucking around with lately. So you can see like this is visualization of memory use on the GPU through time. And so you can very nicely visualize memory use as you proceed through your computation. So typically on a GPU, your computation is much simpler structure. Like you're just taking a block of matrices and you're doing this. And so like, if you looked at this kind of memory profiling of the actual program, you just couldn't see any structure in it. But because it's so structured, what you're doing on a GPU, you can just see it. And I found that absolutely amazing. And I'm happy to talk more about the kind of.
I have a little slide.
Yep.
Is there some pattern in the determinants that appears?
Well, you have to do the experiment. I mean, like, you can imagine, like, this is just like a superpower in random matrix theory.
Yeah.
You just do. And of course, people in random matrix theory have realized this, but other people. Maybe not.
What's the time with the CPU?
Time with CPU,
Would be just for comparison, right?
like maybe 4 seconds or something.
Okay.
So it's like, what's that? Like 1,000 times faster or something? What is it? I can't do anything.
40 seconds.
40 seconds.
Oh no, so it's 100 times faster. So 4 seconds.
It's between 100 and 1,000. depending on-
And just a point here, so like, you know, if you get into machine learning code, what you'll see is that you have some, you know, big training data, and then it's getting shipped across to the GPU and then fed into the model. Okay. And so if I were to do this in a different way, in which I created this on CPU and then I sent it to GPU and then computed the determinant and sent it back, it would almost certainly be slower than just doing it on CPU. Okay? And so there's this big, you lose a lot of time going between GPU and CPU, but the computations on GPU are like can be, you know, almost instantaneous in some examples. And so I think about it a little bit like a quantum mechanical system or something that you can like let operate, but inspecting is complicated. Yeah, so this is one thing that I think is kind of important, which is that, you know, from looking at ML math collaborations, if you have a pure math person who knows no coding, collaborating with an ML person that's not that interested in maths, maybe they write one paper and that's it. Yeah. So it's important that the ML person like is somewhat interested by maths. And it's also important, I think, that the maths researcher is like, you know, knows some basic Python, for example, or, you know, can write some code that generates some training data, for example. And I think it's important to like have a clear picture of where you are on that spectrum between mathematician and ML researcher. And not to think that you're an ML researcher, because we're not, well, I'm not. But also like realizing that it can be incredibly helpful for the people that you're working with to know a little bit. Yeah. So like, you know, with Francois, like I typically get things in a situation where I know that they run on GPU. And then I can say, Francois, like, can you run this on your cluster? Yeah. But if I say, oh, you know, here's some kind of crappy code that I run on my laptop, can you make it run really fast on a GPU? That's then asking Francois to do like 10 times the amount of work. Yeah.
Are there examples where there's an intermediary, somebody who does some math and some machine learning that actually is, or is that not something?
There are such cases, you know, in the Gruen project, the famous Lance Dixon.
Yeah.
And there's Lance Dixon on one hand, who's purely theoretical and doesn't want to know anything about AI. There's me on the other hand, who doesn't want to know anything about QFT, and we have Carl Kramer in the middle.
Okay, right, good. Okay.
So, but the thing is that this person in the middle should be relatively senior.
Yeah.
Don't put a postdoc that has done a little of each. It will just muddy the waters.
Okay.
You don't do that.
That might be a model going forward.
But it's a good idea if you have very theoretical physics
Yeah.
and AI. It's good to have someone who
Yeah.
can speak to both. And I think it should be true in mathematics in some cases.
Yeah, so I guess just in terms of workflow for me, I have my laptop, which is great. And then I have a subscription to Google Colab, but you know, replace that with access to some GPU. And then there is ML Researcher, which is, you know, maybe Francois or maybe DeepMind. And so typically, you know, I'll write things on my laptop so that they work on CPU. And then I'll test on GPU, make sure it runs on GPU, and then Francois does his magic, for example. So this does have a GPU in it, but I've found, so this is the MPS, this is the GPU in Apple's, but it's basically very annoying to use. So there's heaps of stuff that's not implemented. So I was using the GPU in my laptop for a while just to test code to make sure it runs on GPU, but there was so many difficulties that I've stopped doing that.
There are Linux laptops with the GPU, they may still be the collaborators.
No, I mean a Linux, like as long as you have CUDA, then I think it's great.
It's about
But
to do.
but if you're using the Apple GPU, like, unless you're doing very simple GPU stuff, then it's not. As well. Oh, yeah, so that's just a very basic point, like, you know, in ML, we're always tracking like loss, and that's what we learn, you know, in first class in ML or something. But it's like incredibly useful to track other features of your data. So often, you know, you're constructing something in mathematics, so you might be able to record some invariance of your mathematical structure along with training loss or something like that. And the more of that you do, in my opinion, the more you see. And I think that's
How much effort do you put into saving databases of scientific results that you could actually preserve?
I think like training data sets, for example.
I meant things that have some sort of lasting value, and not for one model, but, you know, obviously, you know, data sets of mathematical objects are the ideal case, but, you know, anything that.
Yeah, I guess it's like often, you know, if I think about the combinatorial invariance, you know, we generate a whole lot of Broughara intervals and a whole lot of KL polynomials, but both of those are like extremely easy to recompute.
Okay.
You know,
That's right, that is not worth reading.
and I can't think of an example where, like in some stuff with Adam, we found some very interesting objects, and then, you know, and these are then saved, and I guess we'll.
Well,
keep
like
these.
these isosceles for triangle configurations.
Yeah.
But those aren't,
Yeah, ideally those should,
Yeah.
yeah, and that's, I think, super important. That's it. So, Francois.
Start mine.
Yeah, I mailed you the slides, so you can try that.
Sorry, I'm very untechnical. So I'm following back from, I read all these slides when I wrote mine. It was this morning, so it can be complete, and I knew like these things. Yeah, and I want to talk about two things. So collaboration scenes from my side. And then there's a second part, which are the things I would love to have been told before I embarked in machine learning 5 years ago, which, you know, might be useful for others.
The first few lines of your first slide.
Sorry, I've forgotten how to slideshow in
That's
In
okay, I
Scheme.
can scroll.
Full screen, and then there is a slideshow.
Full screen, presentation. There we go. Okay, so it's called AI for Math Collaboration. It could be AI for Science.
Oh, no, sorry.
Okay, so AI for Math Collaboration. So from my side, I've been doing that for not exactly 5 years, but at least 3 or 4 years. So I got, yeah, kind of a habit. So the first thing is that we are very, very different sociological milieux. So here, since there are many AI people, not many AI people here, I want to state a few facts about AI researchers. So the first thing is that we publish in conferences, not in journals, and there are 3 conferences: ICML, NeurIPS, and ICLR, and you've got to know that you need to pronounce it ICLR. You will sound much more AI if you do that. 3 deadlines: end of January, end of May, end of September. So right now I'm working for ICLR. They are short paper, 8, 9, 9.5 page hard limit. So everything has to be packed there. Those are huge conference, like 10,000 of people, etc. So you expect brutal, noisy reviews by very junior people. ChatGPT has become a reviewer these days, and you can see reviews that are ChatGPT and replies that are ChatGPT too. So it's very bad. There's a harsh week of rebuttal that you can make useful or not. And the consequence is that there are tons of resubmission. You submit a paper, and sometimes it fails, not from your fault, and you have to resubmit it, etc. Also, you have workshop, 4 pages, aligned with conference, easy to get in, but this is exactly the same deadline. And there's a few journals, but typically you submit a journal when you're sick of submitting to conference. So journal papers have been rejected several times. Not always, but it's often the case. Another thing you have to know if you work with people like me that work in industry, we are evaluated twice a year. It's a very competitive environment, so there's an obscene amount of peer pressure, especially on young researcher, of producing something now, tomorrow, in 3 months, etc., etc. You know, what have you done this half, etc. So it's difficult to commit on long-term projects, or you need, you know, a fairly strong character to do that, because you will get a lot of headwinds if we do that. So the takeaway here is that AI researchers think in deadline. What do I do for ICML? And in fact, I'm finishing my IPL, so I'm fighting my co-authors to get them finished and get the base paper possible. And as soon as I'm done, there will be the mating season, which is this moment where all the researchers come to each other. What are you doing for ICML, which is the next deadline? And we decide a new project. Okay, so this is important because it has a lot of consequences in AI teams. So yes, we have large number of authors on paper. This is common. I had, you know, when doing cryptography with Christine Auteur, I had, at one moment we were 4 and working very well. But she's at the top, but she got a lot of pressure from her bosses saying, oh, you should need a larger team because, you know, crypto is important. And I say, come on, we won't function with a larger team, and you know it. It was very, very difficult to fight back. So there's a tendency that if you don't have lots of authors, then what you do is not important. We have a different way of classifying author. So nothing is alphabetical, except if in exceptional cases, there's a first and last author system. So first authors, sometimes co-first authors, are the people who worked. They're typically PhD student postdocs, but not always, but very often they are. And last author are the seniors, so usually they are the advisors. And you don't always expect the last author to work. Sometimes they provided good ideas, sometimes they just add their names. Okay, so the senior authors oversee much more than they contribute, which can be a good thing, a bad thing, but you know, if you have a team with 2 groups, I understand it's very different from what you have in other fields. So it's something that you need to know. All of this, the first, the last author, the number of authors, the senior author, their role, everything is negotiable. You know, nobody sticks by it, stands by it, but you still need to have the discussion. The only thing that is less negotiable is when you work with PhD students, because there's a very strong expectation on PhD students to have a number of first author paper during their PhD, the first year, second, third year. So you need to accommodate for them if you want them to come and play. But the rest is negotiable, you know, the author name, the list, how you do that, the number of people, but it's a discussion that must be had and usually must be had early. So typically once you've chosen where you publish and you've written, you know, you've opened an OLIF and written a plan that you want to respect, this is the right moment to say, okay, who's in what position and who's doing what. Failure to do that early usually cause big clashes just before the deadline, and you don't want that. And it can be really ugly. So yeah, keep that in mind. All the more if you work in the corporate world, because you know there's money at the end of the publication system, etc. There's evaluation and money. So the deadline system makes it possible for us, AI people, to have a lot of papers at the same time. For senior author, this is expected. You know, it's expected that during the first half, you have 10 papers in 6 months. It's expected you have your name. Last MURIPS, I had my name on 5 papers. This is ridiculous. I mean, I didn't work on 5 papers, and I'm not even looking for this. So it's very typical. It's also expected that, you know, young PhD student must have papers and many different papers. So yeah. So it's important if you work with AI people to know where they stand and what they expect in terms of publication. It's, you know, it's enough discussion, but it's useful to have it. And you have to expect disappearances of collaborators or sometimes of whole teams because the deadline appears and they're late. And many projects die this way. You know, people are not there because they have a deadline. And you think, well, they'll come back, and they don't come back. And if you don't come back to them, then the project will just die this way, slowly, silently. Okay. The last thing, or 2 last thing, is that the noisy review process has a very bad consequence, in my opinion, is that it creates a fairly low standard on the quality of papers. because the reviews are short. So many people, and not only the young people, many senior authors work the same way. You have a tendency to say, okay, given the reviews we'll have, this is good enough. And again, no one is forced into this, but there is some fighting back if you want the things to be up to your standards. It's not because people are lazy, but yeah, the typical expectation, even for Europe, so for the big conferences on the quality, quality of the ablations, is very tempting to say, okay, I could do things well, have a large number of models run, to have statistical confidence, have lots of ablations so that my results are good. But if I do this now, maybe I'll get a stupid reviewer who don't get the paper and ask something totally different. So let's wait until rebuttal. And this, this is bad, but this grows on researchers. So this is the kind of attitude, it's not out of laziness again, but it's the kind of attitude you might meet. And yeah, and then the deadline system also has one effect, is that once the deadline is passed and when you finish the paper, you want to move on to something else. Follow-ups are not the norm. So if you want, if you accept a paper as a mid-step into a longer project, you have to say it very early, or you lose the team because in their mind it's done and they're gone and they move to something else. Yeah, I hope I'm not discouraging you from working with us, but these are a couple of things I think you should know. Now, since I have a very nice presentation, I'd like to talk about the failure modes, and I'd like to talk about 3 failure modes that I've experienced many times. So the first one, I call it miss you, miss me. You expect delays, and you expect delays on both sides. I'm not pointing fingers here. On the academic side, you've got the hiring speed, you've got grants. On the ML side, you will have other projects and deadline. I'd like to give you an example with a partnership with SLAC, AI for Theoretical Physics. The first idea with Kyle happened in January 2022. We had our first meeting with Lance on the 8th of February 2022. So it was very fast. We had a meeting at once. A week after, Kyle explained to me what Lance had said during the meeting, which I attended but didn't send a word. And I got my first experiment running in March. And I happened to travel to SLAC in April and present my results. And they were all very excited. So excited that they asked for a grant and got it. But this is the catch. Everything was ready in April. So that was a great project, small team. Then we wait for the grant until October. Then we can hire postdoc thanks to the grant, who arrive between March and July. And then we say, okay, since we have those initial results, let's show them somewhere, publish them somewhere, plant a flag. So Europe's workshop. So this takes summer to, in order to close the previous work. And then someone say, oh, but this workshop paper was very good. Let's make a journal paper out of it. And so that's how you end up 2 years later with nothing more than the initial experiments. Well, papers written, but there's very little more happening. And of course, after that, we stopped working again, and now everything is moving very fast. But you see the kind of delays you can have on a project like this. And this is complicated because half of the team can drop at one moment or at another. Very often, what I've noticed is that projects die because nobody checks in. You stop interacting, and after a while, nobody, and everybody expects the other to come back, and nobody comes back, and everybody's sad about it. So what I think is important is to have a regular communication channel. I'm not crazy about email. I think, Slack, Messenger, anything faster works a bit better because it allows for quick interaction, and we tend to have full mailboxes, so you miss them less. And a regular meeting, even if there's very little to be said, is usually a good system. Okay, but what I'm saying is that lots of projects take a long time. There are long lulls in the project. And I've seen many of those, just dying because people end up forgetting about them. The second one, which I call I want to be like you, is a good failure case when mathematicians do AI and AI researchers do math. And this happened way more, so it's a very bad use of everybody's time. And it happens a lot because it's so tempting to learn math when you're an AI researcher, and it's so tempting. So the harder, my idea is that the harder the problem, the less the AI people should know of it. And it's part of your job as mathematician not to tell me too much, because you might interest me and I might end up reading, etc. And this will be a bad use of my time. It's also a matter of trust. You need to trust the AI guys to do the right choice, and they need to trust you to do the right mathematical choice. As Jordi said, you need to come clean on your abilities. Can you code? What's your math level? You know, it's easy to boast or to pretend, and we always pay for that because basically you expect too much of someone, etc., and things take time, etc. You need also to agree on responsibility. Who codes? Who runs experiments? Who looks at experimental results? Who writes a paper, etc., etc. And of course, at the end of this, since you want to separate the concern, you have the mathematicians on one side and the AI guys, you need a common language to talk about math and AI at the right level. So usually it's sometimes you need, some kind of intermediate person that serves as a go-between. Most of the time it's relatively easy, for the mathematician to know how to dumb down or simplify what they have to say, and the AI people not to get into crazy things about the details. And I think it's important. All of that is negotiable, but very often, there's a very bad case where everybody wants to prove the other that they can do it. And it's so I want to show that I can understand QFT, and the physicist, the physics postdoc in front of me wants to show that he knows everything about neural nets. And we're spending way too much time doing that. The last failure mode is what I call feature creep. It's an expression in software design. So when you design a software in the beginning, it's very clear. You have a nice interface, you have a simple way of doing things, and everybody loves it. And then you start having end users and product managers and all that. And they ask for new features. And you're a nice person, so you develop them. And very soon the features begin to fight each other. Your interface becomes very wrong because there are 20 different ways to do the same things, or the new things for one user provoke bugs in the new things for user two, etc. So this is totally typical. The mathematician will say, oh, let's generalize to this related problem. It's so great. We can do all of this. And the AI will go say, oh, I just read this new paper. I'm so excited to try it now. And this is totally typical in AI systems. So it's really a drag in AI without the mathematicians, because many of our research is junior researcher-led, PhD postdoc, and they read a lot of paper, and the temptation to try every single thing they read about on some old problem is very strong. And so this leads to delay because you end up experimenting, rerunning the same experiment with a new architecture again and again and again, and nothing gets done. And usually, the new model is a little better, but not really better. So you get marginal improvements for incredible amount of work. The other risk is that it usually leads to unmanageable code. You end up with as many parameters for all the things you've tried. And of course, the parameters start to conflict with each other. And code base die from congestion. And the more creative the project and the team is, the earlier it happens. To give you two ideas, the proving team in Meta, Evariste, so that's Guillaume Lamp and all the guys, the Llama guys, very strong guys. Their code became unmanageable in 2 years. The Llama 1 code, I'm not supposed to say that, was considered by the people, very senior people who know all of that, impossible to maintain after 1 year because the team were larger and because they try so many things, etc. So, trying to limit the scope of projects, both on the AI and the math thing, is usually a big service given to those projects because you have two subjects and things can become unmanageable very, very fast in very, very different ways. Yeah.
But presumably one doesn't actually want to not try things. So are what you're saying is that you say that this project we're limiting it, and then those extra ideas are we'll sort of lock this off in this code, and then we're going to try those other ideas on another project? Or are you really saying just don't do those things at all?
No. So what I'm saying is that inside the project, at least, so give you my ML vision of that, is that I tend to be very conservative on everything. And I really play the old guy, which I can do very well. And you get people, oh, we can do this and that, so what do we expect? And we could all work on Llama thing. No, you want to do it, you try it. Usually the person will abstain because it's too heavy. But I try to discourage, too many new things. If someone comes with an obvious new thing that we should do, then we do it. But then if you add to the code, you will need to refactor, you will need to maintain, you will need all that. So it's more, being, conservative, being sort of reluctant to do that. And this is, in my opinion, this is the role of the more senior people in both teams. And I think, when you have a double team, with math or science and AI, the risk is just increased. Okay, so here's, after having said all those crazy things, here's a couple of things I try to do, not always very well. So projects tend to be slow and tend to stop. So you need to work from portfolio because not everything will move at the same time. So you usually.
Can you just hit enter?
Oh, sorry. So you tend to, you want to have several projects you work on at the same time. If you work in industry, you better not tell your manager because they'll be terrified that you work on 10 projects. So I usually hide most of my work. But one thing I like with the portfolio of projects is that they usually cross-fertilize. So you get ideas from one to the other. But it's difficult to say I'm doing AI for science, AI for math, I'm doing collaboration and doing just one project or two projects, because one or the other will be delayed and you'll have nothing to do and you'll drop to do something else, etc. So I have a large portfolio. I try to commit to 2 or 3 projects, not always very well. And I try to decide on time budgets. So what works for me are full days or half weeks. So I say in these 2 days, I'm doing this, or this is my major this week. And I try to think about deliverables. So, okay, this week I want to refactor this code. I want to run this model. I want to do this. I want to do that. But I need to have milestones or ending thing, or I end up having many projects that are sort of floating and I get stressed by that and nobody's happy. Another thing is that you have to choose not to learn and you have to come clean about your limitations. So yeah, I love QFT. I would be crazy about great groups, but I'll wait until I retire. And you have, so it's a complex decision because you cannot not know anything about the subject you're working on, but you have to make a decision on what you need to know. And of course, if you're on the other side, on the mathematical side, you can help, the AI people like me, not to have to know what I don't need to know. And it goes both ways. And that's more for AI researchers, but I think this is AI for science. So the final word should belong to the scientists. So it's about, I'll advocate the AI side always, but where do we publish? Well, you get to decide, or etc. I think it's important. And I think also it's important that, the value of the project is the scientific value of the project, not the AI value of the project. As soon as I start thinking or hear people saying, oh, but it would be interesting to try, say, CANS or Unsearch or anything, because we would get experience with that. I tend to be, not happy about it, because are we doing that for the science, or is it just to increase my ML portfolio or something like that? So I think you have really to prioritize the science in AI for science, and AI is but a means. Okay, I'm sorry, this is very soft, but I hope it helps. So a couple of things I wish I were told in no particular order. So Jordi said it, I'll say it again. This is really an experimental science. You have to think in terms of experiments you can run. As you start working with any projects, someone tells you about isosceles or whatever, isosceles-free graphs or something. What are the inputs? What are the outputs? What experiment can I run? What do I expect from this experiment? You have to design experiments all the time. And the consequence of that is that you need to run experiments as early as possible, thinking long about the project, about the architecture, honing your code until you're ready to run the final experiment is an extremely bad idea. You've got to run one experiment, no matter how simplistic and bad and toyish, in order to get started. The consequence of that is that you are going to run a lot of experiments. And we all pride ourselves on being, intelligent and bright and multitask, but it's extremely easy to get overrun by your own experiments, not to remember what you've done and lose a lot of them on the way and redo some of them, etc. So you need to structure your experiment. You structure them into sub-experiments. You need to document them. So on the personal level, I have a notebook and I note everything I do. And I note, what I want to do, when I start, when it ends, what doesn't run, everything is written and I can come back to it. Inside a team, I like to have, typically a Google Doc or something equivalent with all the experiments that everyone run and everyone push their experiments so that everybody can read, because you need not only to be aware of your experiment, but also of the experiments of others. Personally, I'm not too crazy about the online graphical interface. I mean, they're great, weight and bias and all that, but it's dangerous because it gives you a fake feeling of, you feel secure and you're not. Because you say, oh, everything is in the database, I just need to request something. Yes, of course, but if you have thousands of experiments in the database, you're at square one, you don't know what to request. And the fact that you could possibly have them doesn't mean that you understand anything. It's like owning a very big book about a theoretical subject. You don't know the theory, right? Another thing I do, so this is something I've learned, maybe other people do it, but something I've learned is that every time I run an experiment, I try to write my expectation. What is this going to prove? And I run a lot of experiments just to confirm an experiment I had, an expectation I had, if I do this, I should see that. And I try to write it. Why? Because it helps keeping up and organizing. And it also helps discovering. Most of the interesting thing you discover in an experimental science is when something you expected didn't happen or happened differently. So typically, having kind of a way to say, I ran this experiment, this is what I expected, this is what I saw, I'm satisfied or not satisfied. It looks silly at the moment when you do that, but it usually pays very fast as you have many things. So one thing I would insist a lot is make logs. When your experiments runs, you have to make logs of everything you see, the training logs, the test logs, the results, as many metrics as you can, the number of tokens you've seen, the speed at which the machine ran, the hour when it was run, the errors, etc. You want to log as many metrics as you can, all kinds of warning and errors. It's nice to run graphics on top of the logs. So you run all that and you have nice graphics, learning curves. But sooner or later, you will have to look at the logs because not everything is in the graphics. You can be sure of that. So you have to have very detailed logs and not be afraid of, going into it. And it feels very 20th century-ish, but I think it's necessary. You need to keep a document with experimental findings, notebook, shared document, and reread it frequently. And you need to find a way to keep the non-experimental part of the team informed. It's very, very easy when few people run experiments to have a significant part of the team, even of a small team, that has forgotten the things that were run, and you end up rerunning the same thing or re-asking questions that were already answered. So, when we have weekly meetings or bi-weekly meetings or that kind of thing, a significant part of the meeting is usually spent rereading experiments together. So it's a bit gospelish. You're there and you're reading experiments number 302, and that's how it goes. And I found this really helps. It feels awkward the first time because you're reading the same experiments all the time. But as soon as you work in a team, this really works. So a second aspect, there's a lot of coding. So don't trust coding, beware. Never write anything from scratch. You've read that blog about transformer, you want to write your transformer, do it on a weekend, do it when you're retired, but don't do it in a real project. This won't work because you will write it, but you won't be able to debug it or to solve the problem. You know, debugging Python is hard, debugging tensor is impossible. So don't do that. Never write from scratch and try to grow your code base incrementally from paper to paper. I try every time I start a paper, one of my selection criteria for the paper is that can I reuse a code base I already have? It's not just because I don't want to write new code base, it's because all code base that I've run are solid. New code base that I've written are full of bugs. And the last thing you want is to have bugs, you know, while you are running your experiments, because how do you know what your experiments look like? Good code is extremely important in an experimental science, obviously.
Not doing the training, when you collect the training data, then actually you have to revert again on some aspects of the code, right? So that
Yeah.
And you generate the training set.
So when you generate the training set, this is most of the time new. So for this, you need to test and you need to try to find the easiest way to do it. But when when you have a transformer code and you say, oh, but I want to do this and that, etc., and you want to add some RL components and you have this old RL component that worked, but you have this new idea for brand new, take the old, start with the old and run an experiment and have a baseline with those. And then you can try the new one, because if you try the new one and you got a crazy or a crazily bad experiment, chances are that the result is just a bug in your code that you will never test. And sometimes you discover the code, but if you discover the code 2 weeks before the deadline, then you'll love it. It's one of the worst experiences possible. So you need to use code you trust. So the ones you run on your previous experiment is usually code you trust. You know, the quality of the code is the number of time it ran. And the libraries used by many. Don't trust the libraries. Look at the libraries that everybody uses, because usually those are relatively bug-free. Don't trust your coding capabilities. It's a bad idea because you'll need to debug. And don't blindly trust code from papers. Many people outsource their code. Not all the code is well written. Not all the code will adjust to the new experiments you have. Sometimes the code is plain wrong and the experiments were cherry picked, it happens. But don't blindly trust any code that you can find because it comes with a research paper. Your mileage may very much vary here. The other idea is you can write less and less code. The less code you have, the more likely you are to be able to maintain it. So any feature you don't absolutely need to kill. And it's okay if you want to reuse it, GitHub saves them for you. So it's okay, you can always go to free GitHubs in the past and get the code back. But try to have as little code as you want with small code with as few parameters. And when you need to run the next experiment, don't think in advance. Write the minimal code you need to run the next experiment and nothing more. I'm sorry, I'm insisting a lot on that because it's a very general problem. And finally, okay, it's obvious you need to test before you experiment. What's less obvious in ML is that you need to have the test, the test set to test. So it's usually a good idea, your last project or your last big project where you know exactly how everything reacts is the baseline, the test set for your next project. And so I write a new thing that I've seen in a paper that I absolutely need. I try it on my previous paper. I know exactly the kind of results I expect. And if I don't get the right result, I know I have a bug and I'm not running it. Okay, mind the speed. So Jordan talked about that. Don't over-optimize the code, but keep the code fast. So it's not about premature optimization, but you don't want to prematurely pessimize the code or make the code slow, because you'll see later. An experiment that runs overnight is much better than one that runs over a week. The main reason is that between the time you set your expectation and run the experiment and the time you collect the result, if you have a week, you'll have forgotten part of the expectation if you write it. So ideally, you want to dimension everything so that everything runs fast enough. Okay, and one way to do that is to adjust the problem size by the time you need to train it. Okay, suppose you have a problem size like isosceles rectangles or triangles or something like that. You can do n equals 15, n equals 50, n equals 500. If one takes, say, a few hours, max 1 day to run, take this one. Don't take the one that takes 10 minutes because it's probably a toy problem. But don't go for the one that could take 10 days because it needs, it needs an amount of forward thinking that usually you can't do on a research project. Look also at the sequence length. In the case of transformer, the sequence length is everything. So try to have problems where the models will train fast. When you optimize, there are two things you should optimize. The first one is data loading. So if you think of so you have the GPU, you can think of it as a train, a steam train. You have the engine is the GPU, and the data loader are the guys that are pushing coal into the GPU. You don't want your data loader to wait. It runs on a CPU. You don't want to have your GPU to wait for the data loading. So one thing you need to optimize is that your GPU is always running because you get the data very fast. This means if you read from a file, you need to load the file in memory in advance. You need to have several workers. If you have calculations to be done when you generate the data, do them in advance on CPU and save the file or save the data or do something. This is where you can lose a lot of time. The other area you should optimize are the GPU writes, writing from memory and from GPU to CPU, CPU to GPU is about the same kind of speed loss as writing to a disk with a computer. It's like 10,000, 1,000, 10,000 times slower. So everything you want to load on the GPU, you need to load. There's a there's a function for that, and you need to do that explicitly. Load as little as you can. So if you have a small data that you turn into a large data, well, you calculate, you load the small data and calculate the large data in GPU. If you have a large data that turns into small, you do that in CPU and you just learn the small. You'll gain, no matter the speed of the algorithm, it will work. And all the time, check GPU memory usage. GPU has a large amount of memory. When you overdo it, when you ask for more, your process dies, which is a very bad thing. So you need to know how to never exceed the GPU memory, but never have too much hanging. You must use as much GPU as you can. So if you want to optimize, don't prematurely optimize, but always think that you need to have fast data loading and you need to think of GPU writes. Okay. Another thing, I'm saying that because I've been burnt recently, be careful of Python tricks. It could look like a good idea, you got a calculation to do, let's do multiprocessing. And I had the experience recently in verifying something, and I use multiprocessing because, well, obviously it was faster, but no, because multiprocessing takes a lot of memory, and it takes a lot of, time to get started. And at the scale of GPU and things like that, it actually divided by 3 the execution time of my code, because it kept the GPU waiting. And that was bad. So you need to test this. And I think that what I'm saying here is try not to be too bright when optimizing the Python, because usually the problem is not in Python. The problem is in the GPU and the way you interact with it. Yep. Other things, so think about the training data. You always have to. So choose your project according to the data. If you don't have training data, don't even consider the project. You won't be able to train a model. If calculating the project data is hell or scaling to interesting projects is impossible, don't do it. If you have projects where you have, the state of the art is like SAT solving, free SAT, stuff like that. The state of the art is millions of closes or something like that. You'll never be able to generate that kind of data in large enough quantities or put them into the memories. Don't do that. Another thing you need to understand is the empirical distribution of data. You need to know in advance the length of tokenized sequence, because this is what will break your GPU and all that. So you need to know how long the sequence are. This tells you about the speed of the problem. You have to look for the biases and the non-uniformity. How are your input distributed? How are your output distributed? You have, one output that lots of examples have zeros and pretty much nothing are different from zeros. Then you probably need to balance your data set. So the more you know about your data distribution in advance, the more you can save on embarrassing experiments where you run, lots of things during one night to discover that, yeah, your data distribution is wrong. Try to think very early about data generation, what alternatives you have, how you can have different way to generate your data if you do so. How do you have different way to tokenize your data? Because sooner or later you'll need that. And think of how you problem scale. We always start from a toy problem. If you cannot scale the problem, and I'm not talking about math here, it's really if the lengths of the sequence become extremely large, it won't fit into your transformer. So this is typically a problem that you won't be able to scale in. Okay, so the more you think about the training data in advance, the more you study it, the better it will be at some point. The downside of that, don't sweat the architecture. Go for something simple, go for something you know. And if possible, make it simpler. It's very tempting to end up with a model where you add this and this and this and this and this and that. And not only is it difficult to code and to maintain and to test, and it's slow to train, but very often, one part of the thing ruins the whole thing. So usually when you remove parts of a complex system, you get a better training system. And this is relatively typical. So try to get architecture in AI for science is not the crucial part. It's usually not the crucial part. If your problem cannot be solved with something relatively standard, cannot be solved at all, going for something more complicated will probably not help. And I've observed that many times. So yeah. Last, I think this is my last slide. So there are tons of hyperparameters in the transformer. So there are many, many different things you can try and sweep, etc. So the first thing I haven't written there is that pretty much all your experiments needs to be predicated on the compute budget you have. So you need to know how many GPUs you have, how much time you have, how much GPU hours you have, and how many experiments this allows you to run. Because if you have the time to run 200 experiments, you cannot sweep, all your parameters at the same time, or not in the deadlines you will have. So you need to sweep with method. You need to sweep the important thing, not the unimportant thing, and you need to decide in advance how much, budget, GPU compute budget you're going to spend. My routine is that I usually start with something simple, and I use always typically. So my transformer typically have 4 layers, 5 12 dimension, 8 attention heads. I do that because I did that before. You can start with something else, but I start always with the same. I have the same optimizer, which is Adam, and a learning rate of 10 to the -4, because I've noticed usually it works. I don't add anything, no dropout, no weight decay, nothing complicated. This is my base model, and I always start with that. You can have a different base model. What's important is to have one. If my training curves, so I train a bit. If the training curves are noisy, you've got spikes in the training curves, it's the fault of the learning rate. It can only be that. So you adjust the LR down until you get the right one. Sometimes it's 10 to the -5. If it's very slow, you can try to push it a bit up until the curves get noisy. When they get noisy, it's too high. So usually this is very easy to do. And then you've got the learning rate out of the way and you're happy. That's one less parameter to optimize. Now, if not the training curve, but the test curves are noisy. So you've got training curves that are nice, but every time you test on different data, you get results that vary a lot. Now, it could be just that your test set is too small. So it's useful to say that, because you've got noise, because of the size of the test set. And this is where you might want to try dropout, weight decays, maybe a slightly different optimizer, Adam W instead of Adam, etc. This is typically the use case you want for the optimizer. If when this is ready, you're happy with this you don't need to touch anymore. Okay? Then you can, once you have something that learns correctly in one case, you can start to adjust model size. So you have 3 parameters, but they are correlated. So typically you want to keep in the transformer a constant ratio of dimension to heads. So I typically do 64 because many people do that. But so if you move the dimension, you move the heads. They have to be a multiple of each other. So this is one less parameter. You can sometimes try to have double the number of heads, something like that, but most of the time you don't. And you need to go, so the dimension should usually scale as the square root of the depth. Okay, this is the number of parameters. Okay, so.
You mean embedding dimension or like?
No, the embedding, the internal dimension of the transformer. Okay, and then you want to scale, but not too much. You go for the. So I like to say the smallest model that works. Actually, you want to go a little higher than the smallest model that works in order, if you try a harder problem. But don't try to go to the largest model. One thing you should avoid is when the model becomes so large, it doesn't fit into one GPU. Or when the model becomes so large, you need several GPUs to accommodate the batch size you're working on. Because at that time, you're creating a lot of new engineering problem for yourself. And, it means running on 2 GPU means you need to synchronize them, having larger batches. And if one fails, what happens, etc. So the idea is that if you can keep on the simplest possible model and avoid the things, and if one reviewer asks for it, then you might have to do it, but you'll do it only once. But the less you don't introduce engineering problem you don't have. If you have deeper model, this is where you use skiddling, so you vary the learning rate over time, but this is later things. One thing, so you see, you can do with the sweep on a relatively low budget. You first adjust the learning, the optimizer, so that everything is stable. Once it's stable, you play a little with the dimension, and you have enough. Usually you have enough to be relatively sure about what will work and what will not work. One thing you should do if you have GPU compute, a good compute budget, is don't run just one seed. Every time you have a model, it's randomly initialized. It's a good idea to spend your compute time on running the same experiment with different random initialization. Why am I saying that? Because very often the model is actually random. So the learning is random. So some models learn, others don't. And there's no reason for that. You have to have a fairly good feeling of how likely your model is to run. Because if your model runs 1 time of 2, and you're trying to do a sweep, and it's 1 time of 2, your conclusions are going to be terribly wrong. They will be predicated on the randomness of the runs. So you really need to do that, systematically. And I think this was my last slide. So yeah, so that's what I have to say. I'm sorry, it probably goes in every direction, but I hope you got a few ideas from that. Yeah, that's correct. Thank you.
Can you say what you mean by that?
What?
So the dimension should scale as the square root of the depth. But what do you mean by
The number of layers.
yeah?
Number of transformer blocks.
So
Number, yeah, okay, that's fine.
So basically,
Yeah,
the
and
idea in a
the
transformer is that you have layers
Yeah,
and you have a certain dimension inside, and then you have a number of attention heads.
yeah.
The number of parameters in a transformer is linear in the depth.
Yeah.
And in the layers, it's called L,
Yeah.
and it's like the square of the dimension. So if you want to, sort of balance the number of parameters, there are 2 things. The first thing is that if you increase D too fast, you're going to run out of memory very, very, very fast. So you don't want too much D. And if you want to balance them, the good way is to, sort of balance them this way. So, the typical thing I would do would be to do, say, 4 256. And then I might do
So that
6
means 4 layers.
5 12 layers,
Embedding
4 layers, dimension 256, 6 5 12. Maybe I would do 8 640 and so on. And then I would get here I might get 4 heads, 8 heads, 10 heads, and so on. Try to have a scaling law. It's always a good idea, to say, okay, what I usually do when I want to really do something serious in terms of model scaling is that I decide a relation between those 3 parameters. And I define, this is extra small, small, medium, large, extra large, extra large, etc. And I run those models. And it's usually useful because, the problem is that if you try to move everything at the same time or to sweep on everything, even if you have lots of seats, but that will take a lot of compute budgets, chances are it will be very, very difficult to say something about what you've observed.
You feel about in this kind of math, the situation as far as like reproducibility and people replicating the results. I mean, if we could talk, for example, about something that you and many people study, which is the decimal arithmetic learned by transformers, like generalization, that kind of thing.
So it's complicated because so the conference system and the Hive system. One of the problem with AI is that you can think of AI these days like you would think of finance 10 years ago or consulting a couple of years. You know, every bright young person who wants to make money wants to end in AI. And careers are supposed to be fast. There's a very, very strong pressures to that. So it's a culture of superheroes and all that. You know, the 10x coders, as they say, and those kind of people. So with that in mind, there's a strong tendency to overclaim, to hype everything, and there's a strong tendency even for reviewer to fall for that. You know, when you have a beautiful paper that claims something great with huge results, sometimes caution goes through the window because you so want to see this, especially if it's something expected or something you'd like to read. So I'm not saying that papers are faked, but you can have papers that you cannot reproduce. We had one thing with the Lyapunov function. We had a guy, one of the 3 guys working for several weeks trying to reproduce a small paper, and he could reproduce, they had the code, he could generate the code, and it worked as advertised, except for the results, which were 10% less than what the guys had reported. And I think they run just a lot of experiments and cherry pick the best. But
I mean, in principle, the scientific, community corrects these things, but do you see?
many of these experiments are run only once.
Yeah.
And then you code papers, etc. So it's a bit complicated. Also, you have problem because it's an experimental science.
A bit complicated is perhaps understating, saying it's not satisfactory.
It's very difficult because, you know, you have areas where the test set are ridiculously small. Symbolic regression, you know, people work on a test set called SR bench, which are data set of 20 functions or 60 functions, most of them equivalent to each other. So what you test on that? When you train on large language model, it's even more complicated because how many large language model can you train, you know, for one experiment? Even if you have
It's a problem throughout AI now, because one answer in this math context would be to say that it's all evidence that you use them to prove something, and if you prove it,
Yeah.
you proved it.
Yeah, but you see in the math context, it's complicated because you can see a couple of years ago, I think, there was that paper from MIT people, and there was Gilbert Strang on it. And they claimed you could do linear algebra, so I was interested by that, by generating code. So they trained a model that was, you know, pre-fun search, if you like. And the paper was out, there was a lot of hype. And then there was a silence. And a few months later, I was talking, you know, with people in the branch, and nobody wanted to admit it, but everybody said, yeah, I tried to do it and it doesn't work.
Yeah.
And the impression that it was fake was extremely strong. What can you do? You know, you have 25 authors, you can go to the senior author, they will tell you it's a full
the
PhD.
traditional way that the physics, at least, the theoretical physics, or the more theoretical side comes with that is to review article, right? That we just accept that the primary literature is not 100% reliable, and of course, some people are more reliable than others, but then people really put a lot of work into writing these long and more careful review articles where they give lots of space to the correct results. And if they don't say something incorrect, they do kind of say, well, also see that, you know.
I've very, very rarely seen this happening.
Exactly.
There's been some effort by people not doing exactly what you want them to do, but there's been some effort to try to see, for example, are we overfitting to like a benchmark and things like that, and like basically testing a lot of architecture that has been proposed throughout the years and seeing, and there's some variation. There is a signal when people are saying these things tend to work more and people tend to use it a lot, they tend to work. So with some people doing that, I think it's just a question of like collecting when you testing data, when you benchmark and doing all of this, and it's not rewarded a lot. So very few
Yeah.
people do it.
And if you fail to reproduce a paper, you know, there's always that
Yeah, so-
nationality, maybe you haven't
Well,
understood it.
That's right, you can't expect people to spend a huge.
No, but
amount
they
of time
tend to
they have
try to
spend some.
produce like architecture ideas and things like that.
Yeah,
And those have been done. There's been people like in Stanford doing this systematically a bit. So those things happen,
yeah.
but they're not very
Yeah,
rewarded.
yeah, I mean, in physics, I wouldn't say it's incredibly high prestige, but it's definitely prestige, there are prestigious review journals, yeah.
Yeah.
But also like the scale of the number of papers published a year
Yeah, that's.
doubles every year. It makes it.
Well, not all
impossible to
results are worth.
No, but there are things, that, you know, there are things that you can be sure, of, because the market moves fast, so many people have a kind of an attitude saying, okay, when you have a new paper, you got the hype, etc., especially if it comes from big labs, you know, anything that comes from Stanford or from DeepMind or from us, etc., tends to be accompanied by an amount of hype that is totally unreasonable. But then many people try to reproduce it.
Yeah.
And then you see relatively fast of papers that have been, you take the Cannes paper. the
Yeah,
one
yeah,
Fabian
yeah,
is on.
that's right, that's.
A week after Cannes, there had been 10 tries and
Yeah.
people published and showed things.
Yeah,
So at this point, you can say, okay, everything there is validated because
yeah,
it's
yeah, that's
produced.
right.
I like to talk about fund search. Fund search is more complicated, but to me, fund search
It's
is,
kind of the things in between. There's the-
Yeah,
the things that
exactly.
Attract a lot of attention, and those get checked, and everybody hears that there's something on. Then there are things where nobody cares anyways, and then there are the things in the middle where. Yeah.
the problem is that you have experiments with things that nobody really cares enough about, so they never tried,
Yeah.
never really
Well, that's
reproduced.
that's not a disaster if nobody cares. then nobody
No.
cares.
But you see, you have this situation of things that have been reproduced and work, and everybody is happy about it. You have those papers that, you know, many people try to reproduce and didn't.
And then.
And then there's usually a-
If you hear that, and if you're not in the community, you're not hearing it. So that's where.
Yeah, this is true. And then you have papers in the middle for which, yeah, you don't really know. So
Anyways, it's coming a bit from the outside, it's an observation and something that.
yeah, it's even true for the, you know, for the code. If you go, for instance, to Hugging Face, which has a lot of, you know, code that you can use. My experience with Hugging Face code is that it varies a lot because you have, for instance, the tokenizer are used by everyone. They work. Those one you can trust them. But I've been using, you know, some